Okay, hello guys. Today we have space and times number 6. And okay, what questions the previous ones? How was the questions? How you've done them?
They were good.
They were good. You managed to find everything. Okay, good. Then I remember that there was one question in the previous one. Remember that we had some issues that we.
Yes, right. And we did not solve it.
You didn't find what was it?
Still don't understand.
Okay. So I'll remind you, just give you just few words, right? It was about general things about the general understanding of motion. What is motion in the general, not the motion like a particle going, or maybe a wave or whatever, but any motion, any. So it's very very abstract concept. So, and we were talking about that when something is changing, right, and the subject or reference frame of reference is like not changing, right? So we have something like the time is running because the change is going on, right? And then it goes to a certain point, like from 1.0 to 0.1, right? That was starting point 0, right? And then what happened actually? We repeat it again, and to repeat it again, we move the subject or frame of reference to this position. Remember that? There was talk about this. So this is changing the outside world. Something is changed, and the time is running then because something is changed. And then we move ourselves. We change ourselves. In this case, when we change ourselves, the time looks like time is running in opposite direction because everything is relative. So when the things was going on changing this way, it was time running like that direction. When we move ourselves here, it looks like the time is running that direction, opposite. But anyway, the result is that we are standing on this point 1, right? Already, we're looking from this point. This is now a reference point. It was before we were here or here, whatever. And now we're here. So this becomes like the new point 0 for now, for the next step. So this was the first step, then the next step. And then it repeats, the process repeats so again and again. So this is like point 2, this is point 3, and all the time the subject or frame of reference is moving too, because this becomes the 0 point, then this becomes 0 point, then this becomes 0 point. Remember that? No, I was talking about this. Just I'm trying to remind you this. So this is how the process of change or time running. This is how it's you may display in general. Like we look at it in general. Whatever change. This is like abstract change. Whatever changes. We don't know what is changing, how it's changing, whatever. But one of the cases is like the movement, the movement of the particle, for example, movement of some stone or whatever, or maybe quanta, whatever. And this is the changes of our subject, so the frame of reference. So that was the thing that I was explaining, was talking about. And the question is, then because we're changing each time to the next point, we're changing our frame of reference, right, to the frame of reference. So ourselves moving, looking from here to here to here, to repeat the process again and again and again, right? And the process is still the same. It's just from 0 to 1, here again from 1 to 2, from 2 to 3, whatever. Remember this counting process when we're talking in the math lectures is the same thing. The same thing is counting. Counting goes the same thing. So we count from 0 to 1, then we count from 1 to 2, but it's the same, like we move the same pattern here, then here, then here, the pattern of counting. The same thing is in anything, in physics too. So it's repeat and repeat and repeat and repeat. And the question was like that because we're repeating and everything is the same. And remember in physics, the idea of relativity, it gives the result that everything is identical. Okay, all particles are identical, all speeds are identical, like totally identical. You cannot distinguish one from another. So the question was, okay, we are looking at maybe process right here, right? From 2 to 3. But what happens here from 1 to 2, from 0 to 1? Are they just totally forgotten? Or what is happening? They are the same, remember? The same thing. Okay, we moved here, our frame of reference moved here. But what is going on around? Outside of our frame of reference. Are these changes still going? What do you think?
Yes.
All these things are identical.
They must, we just don't see them.
Yeah, we don't see them. We will look at this, right, at particular place. But and that's why we see how the particle or whatever moves, right? We see the particles moving. But what's happening in other places? We don't see them, but they're the same, identical. Something should be happening there. Just we cannot just observe, right? So you understand, guys, what I'm talking about? Eh? Katya, Vitya? Huh? Kinda. Okay, you'll talk to Daddy and you'll think about it. Just think about it, right? And was suggestion that yes, something is happening here too. Just we can't see it, right? So it looks like that it's correct. The answer looks correct, but think about it. But one of example of such things is the interesting phenomenon that was found not recently, but not that long ago. Maybe 20 years ago, something like this. It's like modern physics, totally like the front, the modern front of physics, like the frontier. So, and what was happened? What was found? It was found that our universe, at the very beginning, at the first 10 minus 32 part of the second of its existence. So it's
32 seconds.
it 1 divided by 10 to the power of 32, right? So it's like 0, 0, 0, 0, blah, 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 1, and this is like 32 zeros or something, right? Seconds. So it's this part of the second, and this part of the second right at the beginning of the universe expanded. It's like it was actually before Big Bang. There was no light at the moment. There was something else. This was like the foundation of Big Bang. It's considered the first part of Big Bang, but we cannot even see it. We see the result of Big Bang. It's called microwave radiation. Remember this ancient radiation that we were talking about? Yeah. You can see it on old TV, like a foam, like a snow. They call it snow. It's called white noise. So this microwave radiation. So for this part of small second, universe expanded in size in 10 to 26 times. Can you imagine this? For that fraction of a second, it expanded 10 to 26 times big.
But doesn't this imply that the original size wasn't 0?
No, it was not 0. It was so-called Planck size. It was about something, I forgot the something 10 minus 32 centimeters or something like this. You can look at this. It's Planck size. This was the beginning. Huh? But anyway, it's expanded to 10 to 26, and this, so it's an explosion like unbelievable. You can't compare it with anything, right? And exactly at that time, all the matter was created. Matter as we know it. It is called the epoch of time, right? Epoch with the duration of 10 minus 32. Can you imagine epoch of that duration? So
Yeah.
it was epoch of so-called baryogenesis. Baryo from baryons. Baryons are particles of matter, like neutrons, protons. Actually, together with them, electrons were created. So, and they were created about 10 to the power of 80 baryons, electrons, whatever. So this all this thing, this epoch is called actually inflation. It's called universe inflation because it was so fast, faster than any explosion you can imagine. So this was inflation. It's called inflation. The origin of inflation, official science does not know. It's experimental result. We just know that that was the case, but modern physical theory does not explain it. The only thing which explains it is this absolute relativity that I was speaking before. Exactly that what we're talking about right now. That something is happening, so many things. So what is going on there? Actually, what is going on there? The particle returns to itself, and when it returns to itself, there are double of them, right?
Oh, you told me about this thing.
Yeah.
It goes back in time.
When you go back in time, you see yourself, right?
Yeah, didn't you say
Yeah.
it goes back in time, gets itself, and it goes back to the present?
But interesting enough that when you go back, there are two of you, and you are identical, right? And both of you are in time, so the time continues changing. So after the second thing, there'll be how many of you?
3.
4.
You double it. Oh,
You double it.
Wait,
Now the 4 are doubling, right?
But not identical. Their age is different.
Yes, right. But according to physics, they're almost identical. Remember, the ages, yes. These things, these circles are actually coordinates. There's a space and time are created at the same moment where the matter is created. So inflation is this doubling and doubling is in geometrical progression. Actually, it's even faster than geometrical progression, but we don't speak about this. So this process causes inflation. Just for you to think about it, okay? So, and that's it for it. Just think about it, and this is just okay. Question on that? Short. Not. Okay. It was abstract talking. We will sometimes return to such things to explain, but right now we'll continue on waves, right? And we'll talk about reflection and standing waves. It's a very important thing, just a little maybe ahead again of many things, but it's good to understand at least something on this, so we will talk about this. Reflection and standing waves.
But, I'm sorry.
Yeah.
Before we carry on, I actually had a question about the questions.
Sure.
The third question called for the pattern on the wall when you send one photon at a time.
To the what on the wall? Say it again.
The pattern on the wall. You know the experiment with 2 slits.
And what is on the wall?
The pattern from the light. You know how you have two. You put a blocking wall with 2 slits through which the light goes.
Okay.
And then the pattern on the screen behind it, right?
Pattern. Okay, pattern. Okay, got it. Mm-hmm.
And the third question called for that kind of experiment, but with a single photon sent at a time.
Yeah. Okay. Mm-hmm.
So it sounds like there should be just an even glow on the screen.
Why?
Because the photon, if it acts like a particle, it will just flow through the slits randomly, here, there, whatever. But in reality, if I recall correctly, you do get the pattern there anyway, because photon behaves like a wave.
Yes.
Right?
Yes. Okay. Exactly. Mm-hmm. So what was the question?
Huh?
What was the question?
Is this correct?
Oh, yes. That's a very paradoxical thing. Yes. So still, when the particle goes like the two slits, right? The particle goes. It goes all the time through only one slit. It is known. It is checked. Experiment shows that each time particle, the quantum is going only from one of the slits, not this together, one or the other one. It goes like, for example, to this one and goes to the screen and it hits here and there is a dot. So it behaves like a particle. It goes to the dot. Bams, that's okay. Okay, the one has passed. Now when it's already gone, we generate another one, right? It goes, like for example, we go again through this slit. It goes here and again there's a dot. One dot. No like diffuse thing, no diffuse picture, just dots. Here dot, pass through the slit here somewhere. We don't know through which one slit. We cannot do that, but we know that it passed through one slit. When we put registration here and here, we know that it goes only here or there. There was never like in two. Like if you put two registration points, like two cameras here and here, they never work together. Only one register or here or here. Each time goes through one slit. Okay, another dot. Maybe it goes through here and dot is here. Again, dot again. And like we do this again and again and again, only one quantum goes through. Boom, bam. Then another one goes, boom, bam. Dot. But when the dots summarize here, we see this pattern, the wave pattern. So here is maximum, lots of dots. Here lots of dots. Here lots of dots. Here almost nothing. Here almost nothing. And there again, lots of dots. You see? That will be on the screen. If we have a photo, it will be like this. Like here is black, here is white, here is black again, black again, black again. So this is a wave pattern, like a waves. You see, nothing here, nothing here, nothing here, but here, lots of dots. So somehow they behave like a particles, like a stones, and the waves at the same time. Okay.
Yeah, Papa said the reason this happens is because of the way they go. It forms a triangle, and so the reason the middle is always bright is because it's an isosceles triangle, so it always has the same distance to travel, so it's always bright. Constructive interference.
That's for the first question when we were.
Yes, there is. It is explained as like. It is explained by the wave ideas, right? It is constructive interference here, and here, and here is destructive, here is destructive, here is destructive, right? It's correct. The interesting point is that still there are particles. How they can be waves? Wave is just like everywhere. Like imagine a wave, like in the ocean, right? It's a huge one, right?
Yeah.
And the waves like we have one photon, right? Okay. It can be registered as a particle or electron as a particle. And still it's a wave which actually is everywhere. It's everywhere in space and in time. So it does not have any size. At the same time it has size. So this is a paradoxical thing which actually mind-boggling and transformed the brains of physicists like for a whole century. It is considered that it cannot be understood at all. So like the brightest physicists of 20th century, they say it cannot be understood. Cannot be understand or understood. What's the grammar of this? Understood. Okay, so this is the paradox. So you should, for now, just understand this is paradox. And the explanation is about this picture of actually going back in time. It can be explained. It can be shown mathematically and everything, but it's not. Right now. It is not official science. It's very close to it, but not yet. Okay, so and this idea of this. Remember this absolute relativity. Remember? So it's an idea which explains a lot of things of modern physics, lots and lots, much more than even I told. But right now it is not like yet accepted everywhere. Okay, so this is last question for this. We can start.
Yes, thank you.
Okay, now, okay, standing waves, reflection and standing waves, right? So there's an interesting thing which happens when with the waves. The waves like traveling along like in the space, right? And of course it's changing time. So it's like wave like on the in the ocean or like sound waves or electromagnetic waves, radio waves, light. They all electromagnetic waves. So they travel in space and time, and they can be reflected, right? From something. Like there is some obstacle, like a wall.
What?
Like,
Oh yeah, these are called
yeah.
oh yeah, standing waves because then they go the opposite direction and then they
Yeah.
crash with the other way.
Yes, if you really look at something where the wall in the ocean, right, like a wave breaker, right, and you see the waves coming like this, you may notice that there are also waves going like this.
Yeah.
So this is a falling wave and this is reflected wave. So waves are reflected actually. And the laws of reflection are very similar to the laws of reflection of light. It's like the same angle reflected. It's this alpha and here alpha, the same angles. So going like this and reflected by this angle. It's symmetrical to this perpendicular line, right? So like this, and this is reflected wave.
So
This
always
is
in the story,
yes.
the angle of reflection has symmetry.
Has what? Yes. Yes, it's symmetry. Yes, of course. Yes, this is a very. It's a symmetry. Yes. So this is like a symmetry, like any mirror do the same thing. This is the wall works like a mirror. So waves coming back and falling down and coming back with the same angle, right? And but also there are some wave features here which we were going to talk right now. So now let's talk about like this. We have a wall, right? And there's a rope. And here we are standing and holding this rope. And the rope is fixed here. And we do like this, you know, maybe you've done something like this with the rope. You're waving this part of the rope, waving.
Oh.
What you will see? We'll see the wave, which is going like this here.
Yeah.
On the rope, right? And then if you really you know put your attention, you will see that wave come here, and then it goes actually back. It reflects from this point.
Yeah, I've actually seen that.
And it goes. You've seen that, right? Okay. So it's very easy to see. You may make this experiment at home. It's very easy to find out. But there's interesting thing. You may notice it that when it reflected, right, it goes like up. Like for example, your rope goes up, hit the wall, but when it's reflected, it goes like this, opposite. If you make a one wave, like for example, like this, you know, without this thing, you will see that it goes opposite. This opposite, it means that the wave change, the phase of this wave is changed by pi. It's called delta phi, the difference, the phase difference.
Yeah.
So it's pi. So it's changed. So the wall somehow changed the phase of the wall of the wave. And what is going on here? What is going on? It's very interesting because this point is totally fixed. How can this be? The rope is vibrating, right? And the wall is standing. Nothing changes with the wall, right? So okay, vibration on the rope goes here, then it hit this point, and somehow it got reflected. How can this happen? What do you think?
Well,
The idea?
Oh, yes, this is like the standing wave. It reflects back.
Yes, it's the same. It's the same thing. It is reflecting. Yes, standing, not standing, whatever. But we're not yet talking about standing. Those are running waves. Right? Those are running waves, like the waves that hit the wave breaker in the ocean, right? So those are running waves. So the running waves change the phase by this factor, delta phi, right? It changes it by pi. But how it happens, what do you think? What happens here? Okay, the rope is blah, 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 vibrating, hits this place. This point is not vibrating, right? Here's the wall. The wall is hard. This rope cannot touch the wall, right? The wall is still standing and very hard. So what happens in this point? What do you think?
I don't know.
Huh?
Could be that it's sort of like the rope is sort of like a slingshot. It tries to pull that fixed point up,
Okay.
but instead it's being pulled down.
Why?
Well, you pull it if you take rubber and you fix the bottom of it to the table and you pull it, and
Rubber.
let go, it will go down.
Oh.
Okay, rubber, right, but it's not rubber, it's like a stone.
No, the rope itself is elastic, right?
Oh, the rope itself.
Yeah.
But still, if it's rope itself, but still the end of it, it's still here in the wall. It's fixed. It's really fixed.
But what's happening is when the wave comes, it tries to put that fixed point up.
Okay.
That's what the wave does.
Okay.
Right?
Yes.
And but the point cannot move.
Okay.
So the elastic rope stretches as much as it can and then bounces back down.
But still, no. But still, the point is not moving, right? So, what's going on here? Any ideas?
So the point is not moving, but the attached rope, while pulling up.
Guys, maybe we can cut his idea. What happens here? I can give you a clue. Think about Newton laws. Newton laws. Remember Newton laws? Laws of mechanics.
Yeah, this is the third law.
Aha, okay.
That's what I said.
What about, okay, you didn't say that. Okay, yes, the third law. So when the rope actually, here rope, it pushes the wall, this way, the wall pushes this way. The wall is the opposite, the third law. It's a response, right? The wall actually pushes the rope in a different direction because they're...
But then how come it's going like down though? How come it's
Because it's opposite. The rope tries to push the wall up because it goes this way, right? The wave on the rope, it tried to move the wall. It cannot really move the wall, but it tried to push the wall up. But the wall by itself, because it's the opposite law, it tries to pull the string back, and that's why it goes. And that's why there is the law of reflection from the so-called hard reflection. It's called hard reflection. Hard boundary, actually. Hard reflection boundary. This is hard boundary.
Wait, so
Uh-huh.
so the rope is also trying to push it up, so the wall pushes it down while pushing it in the other way since it's going in that direction, right?
Yeah, the wall pushes the rope back because the rope tries to push the wall. That's the third law, right? That is correct. Yes, it's the third law of Newton's law, and it gives you this idea. So the same thing, like it's maybe easier to understand that when you have, like for example, again, you have this like the tube, right? And there's a hard wall here in the tube. This is the tube. And there are air waves. The sound goes here. Air waves are vibrations like this, not like this, but this. Pressure here, pressure back. Pressure here, the pressure is more or less, right? Here. And when it comes here, the wave comes here, it presses the wall this way, right? The air. When the wave comes, it pushes the wall here. But according to the third law, this wall pushes the air back, and then you have reflected law, reflected wave, which goes like this.
Oh,
So-
isn't that why we have storms? Because something pushes it back into each other. They are warm in the hot air, and then it forms a cloud, and then.
Maybe you're correct. Yes, in many ways you can see these patterns. If you look at the clouds, especially in the stormy weather, when It usually you can see it's a prediction. If you have this, I forgot the name of this, some sort of a scattered clouds like this, you know, like they have these patterns of the clouds. You probably saw that kind of clouds.
Oh yes, I'm sorry,
This is exactly this interference, because yes, wave goes and then reflected somewhere from the fronts, because cold air and warm air has different density. They form boundaries, which actually reflects the waves in the atmosphere, and the waves they form these form of clouds, and they are prediction of storm. So you're correct. Somewhere the storm is going, and the storm generates that kind of clouds.
A question about the air pressure. When it bounces back like this, does it invert the phase?
Yeah, yes. Here exactly. It's the same thing. Yeah. In this, it is called hard reflection boundary, and delta phi is always.
No, but this is different though, because if you take a look, for example, at the waves in the ocean, and when they hit the wall, they don't reflect. It's not. They don't invert the phase.
They do.
No.
No.
The boundary is not hard.
No. If you no. If I'm talking about the wave breaker. It's not like it's not if you hit just the sand.
Wall.
The sand is not that kind of thing. We're talking about the wall. If you watch the wall, yes, it's opposite. Yes, you'll see. Just.
No, that's not true, because it's not a hard boundary, because the edge of the water can move along the wall.
Sorry, but
And it's not pulling the wall up or down, and the wall does not.
You're talking about that's not fixed, right?
That's right. And
The-
the same thing here.
Okay, guys. Maybe you're correct, but we should this is a point we should investigate, because the waves in the ocean actually they're not that simple. Like in the rope is one thing, and you're correct that the point is that they're fixed. This point where the rope is connected to the wall, it is fixed, right?
Right.
But wait. Just let me finish, okay? But for in this case, we have this. It's called longitudinal wave, which vibrates like this, in direction of movement and back, right? This is the sound, like sound wave, right? But the waves in the ocean, maybe partly you're correct. In the waves of the ocean, there are certain things. The wave in the ocean, the movement of actual particles in the wave are actually like this. It's not this or that. You see? The movement is both this way and that way. So I'm not sure, actually, you're maybe correct. I'm not sure what actually the difference of phase is in the wall. My guess is that it changes, like pi, but maybe not. So you maybe better to dig it and find out. It's one of the questions. Take it and try to resolve it. Find it and maybe in Wikipedia or whatever. So it is the waves in the ocean are more complex. They are they're not longitudinal and not, what's this name for this? I forgot the term for this.
Latitude.
Huh?
Latitude.
Maybe latitudinal. I don't know. Oh, altitude. Latitude. Maybe latitudinal. I forgot the term for this. So investigate this, okay? So, but you got the idea, right?
No, I still have a question about the pipe.
Okay, sure.
So let's suppose a high pressure front comes, just a single one, right? In
Yeah.
that pipe.
Okay.
And it travels, hits the wall.
Mm-hmm.
When it goes back, it's still high pressure.
Yes.
So it did not flip the phase by pi.
But believe it or not, it still changed the phase.
How?
No. That's more complex thing, more complex thing. Okay, maybe I can explain. It's difficult to explain. The phase when you will have a single, we're talking about single thing, right? Single thing.
Yes, one.
When you talk about single thing, it's difficult to talk about phase in a simple thing like a string with the longitudinal wave. Very difficult to talk. It's not exactly correct to talk about phase here because it's difficult to define the phase in this case because there are lots of things happening. But okay, but that's a good question. Still I can tell that phase has changed. It's opposite. But you're correct that the reflection would be there's no difference, right? In the rope you have up and down. Here you have only the pressure, right?
No,
So
I
in
think
this
it's
case,
because it's longitudinal. If it's going in the opposite direction, maybe that's the phase. Or anyway, okay.
Hey, Dad.
oh yeah,
I also have a question.
okay, sure.
Let's say there was a wind in there strong enough to break the pipe. I meant the wall.
Okay.
Would the force of the wall trying to repel it actually slow down the speed, or would it slow down but then accelerate back to normal speed?
Okay, there's an interesting question, and of course it's a very complex one, right? So we'll try to explain it. We'll turn to another type of reflection, right? Which is called soft. Soft. And soft is quite opposite. It's open tube. There is no wall, right? No wall. Waves are going this way, goes through, and then goes like, you understand this, according to Huygens principle. Okay, they form some sort of spherical wave outside the tube. But does reflection happen here actually? What do you think? Or not? The tube is totally open. Waves are going this way, and
I know it does.
no, you know what guy's thinking.
What do you think?
But how does it create refraction?
Yeah, I don't know how.
Yeah, like how does it create refraction when it's just going through the tube?
Reflection.
Reflection.
Oh, sorry, reflection.
Yeah.
Because it goes on the tube. There's no more wall.
Yeah, right. That's interesting thing, right? It looks like I have some maybe sort of a clue. Maybe you can find another one. You think about it, right? Not sure about the term, but when you're boxing, when you miss the body of your partner, right? You try to hit him, right?
Yeah.
And when you hit him, of course you feel the hit, right? Not only your partner feel, but you feel too with your fist, right?
Yeah.
But if you missed, what's happening? You goes this way, right? Further, but then you stretch, and your own stretch actually make you back.
Well, yeah, because then you. Oh yeah, Papa. So this is for example when you stretch a elastic band too far, let's say forward,
Mm-hmm.
then it just snaps back the other way.
Exactly. So this is sort of a mixed heat, right? And the air stretches too fast, and then it has to contract again. And that actually really it is like your dad said, it creates reflecting wave.
I see.
It is not.
Oh, that's exactly what Peter said, actually. Yeah.
Yeah, it is not that strong, of course, like in the previous way, right? When they have hard boundary, it is called soft boundary, and it reflects. And actually here, delta phi is 0 actually, so there's no phase change. There's no phase change. That and yes.
How would the air, like I felt it before,
I'm not getting what works.
When you open a pipe,
Uh-huh.
the air when it comes out is actually stronger than when you feel the inside. You know, like let's say you open it, the air comes
I'm not
out.
talking about opening when the wave is going. It's just open tube. It's very opposite experiment, right? It's the open tube, and now you're pushing the wave here, like the open tube. So it will go straight. It will go here, spread here, but also it creates the reflected wave too. And it creates because like a mist heat, right? So the heat mist and your own body takes it back. So the body of air here actually pulls part of the wave back because it's
I have a very good example. Like analogy, like when you fire it right away when the stretch too far, it pulls back again.
maybe I didn't hear.
You know a slingshot when you pull it and let go, so the elastic band goes forward.
Yes. Even slingshot. You're talking slingshot, right? Yeah, right, exactly. Yeah, exactly. It's the same thing. It's elastic thing. It's the same thing as Daddy told before. Remember talking about the string, that about elasticity of the string and trying to explain how it reflects from the heart. But here it's exactly that, but it happens only with a soft boundary. Because actually there is no boundary, right? And another explanation for this with a string, is like that kind of picture. Soft boundary. That's that kind of picture. When you have, like, you imagine you have a rod, right? Metal rod, and there's a sliding ring here, right? And your rope is connected to the sliding ring, and here you are. So when you produce waves, right, this sliding ring goes up and down.
Oh yeah.
So it's not fixed. You see this, the movement is not there's no restriction like for the movement up and down. It's easily moving. And still reflection is there, but delta phi, the phase change is 0 here. And okay, and returning to your question, Vita, remember that you destroyed the wall, right, or whatever. It's a mix of both cases, right, and very complex one. So the wave is going, then the boundary, the wall is destroyed. So partly it is reflected, partly it goes through, and the phase is partly changed, partly not. So there are a lot of different type of waves actually generated in this result. And when you're trying to understand what is going on in the reality, you should take into consideration all these waves, calculate their amplitudes and everything, and combine them because of the superposition. Combine them, and you have some result. But it's a more complex calculation. Did I get some explanation?
Oh, no, sorry.
Do you understand what I said?
Yeah.
Okay, so it's just more complex thing, but you can combining two things like soft boundary and hard boundary, right? And also calculate what's the change was. So before it was hard reflection, then it broken. So some wave goes through, some wave reflected from the parts of the broken wall, some reflected from the open space, right? So no soft boundary. They all summarize together, superpose to each other, and you have the result. Result is complex, but it can be calculated. Okay. Okay, guys, what we have here. Okay, I wanted, but you said that you calculated. Antosha, did we have a talk in math about sine, cosine, and
No. Well,
Huh?
We talked about, they know about right angle triangles,
Mm-hmm.
but
But
they're definitely not very good with trigonometry.
what about similarity in triangles? Okay.
Congruent, yes.
Oh, it's called congruence? Okay.
Yeah.
Congruent figures, right?
Yes. You know that.
Like
Right.
triangles. So, first of all, like we have a triangle, right? With the right angle here. What's the name of these triangles? Right triangles?
Triangle. Right angle. Yeah.
Right triangle too?
Right angle triangle.
Okay. So, and for example, the big hypotenuse, what's the term again? Hypotenuse. Like let's denote it R, right? And here is A and here is B, right? There's a definition. If R equals 1,
A squared plus B squared equals R squared.
so sine of angle alpha is A, so it's because R is 1, right?
Oh yeah, now I get it. Because then they would both be equal. They would all be equal.
Because R is 1, yes.
Yeah.
And cosine is B, so this is called, believe, opposite, right? Opposite side, right?
Wait, sorry, I have a question.
Or just wait with the question. Is it called opposite side? This A.
Legs.
Oh,
Legs.
huh?
Legs.
Opposite, yes. It's an opposite leg. Yes.
Opposite what?
Leg.
Oh, leg. So it's opposite leg. So opposite leg divided by hypotenuse, right? And cosine is adjacent, okay?
Adjacent.
Adjacent divided by R, so again, it's B, right? So those are things. And what was the question, Fitya?
Oh no, it wasn't a question.
Okay.
I answered it.
You answered?
Yeah.
Okay, so this is like definitions. Those are definitions of sine and cosine. Just if we didn't talk about it, just remember this, right? So those are definitions. And when we talk about congruent triangles, right? If we increase the size of the same triangle, everything the same, just increase the size, like the scale. We'll have that kind of triangle, right? And this R is already not equal 1 already. It's some R, right? Right?
Yeah.
And for example, we increased the whole scale. We increased like by the factor of, like, for example, what? Like K. The scale. We changed the scale. So maybe twice as big, right? So this will be Ka, right? This will be just K, because was 1 here, this will be just K, right? And this will be KB, and the same angle, because it's all just pulled like this.
Understand? Congruent.
Congruent, yeah. They totally the same triangle, just the size is different.
Does you get it?
Yeah.
And you try to do the same thing, like you divide this, Ka, divide by K, by the hypotenuse. What you will get? Still A, right?
A divided by K.
Or it is sine alpha. So with the congruent things, the angles are the same, and of course sine and cosine are the same. And that's very, very significant result. That's why we use so often sine, cosine, and all these trigonometric functions, because they work for all these congruent figures. Whatever you have, you still have, if you take the opposite thing and the hypotenuse, opposite leg, and hypotenuse divide one each other, you will have sine or sinus of alpha. This is very important thing, just for you to remember and to remind. And one small thing, I don't know, you said that you solved, you got the formula for a double slit experiment? Remember, was a question?
Yeah.
You got it? You understand, right?
Well, we didn't derive the formula. I think actually it wasn't the form. Well, you can't really derive a formula there. You need to figure out where the bright spots and the dark spots are, and that depends on the wavelength, the distance between the slits, and the distance between the wall and the screen.
Okay, I'll tell a little just for you to be in the same phase, right? That we have double slit, right? Experiment, right?
Yeah.
There's a walls and there are two slits, right? We have waves coming here, and this is lambda, right? This is usually lambda. It is the wavelength, the distance between two maximums of amplitude, the curves, right?
The distance between two identical phases.
Yeah, two phases, yeah, whatever. Yeah, two phases, but usually it's easy to say these are maximums, right? They're going maximums, right? They're divided. The difference between them is lambda. They hit the wall here, right? Here, the first maximum, right? Hit the wall here. It produces something here. We would not talk about this wave. It goes like this. It produces something here, and the wave is spherical. Remember? And for example, it goes, and when the second maximum comes here, from here this creates like this. The spherical wave. Remember this Huygens principle. From here goes spherical wave. And here, this maximum is already here. The second. This is second. This is first. This is second.
Yeah, you gave this as homework. We did that.
Yeah. So you did that, right?
Yeah.
So how to calculate it? Here is the alpha angle here.
Yeah, we did that. Yeah.
We did that. So and we look like this. If we talk about the waves that are coming here on the center, they're all in the same phase. All in the same phase. So they come here. There's the same phase. When you have some angle here, this difference is exactly lambda, because the wave, the same wave, right? But here spherical is lambda. It comes here and creates that kind of wave moving this direction. And the only thing you have to do, that this thing should be in phase, or delta phi should be 0 or like 2p, 2 pi, or whatever. So they just maybe just lambda. The difference maybe just lambda. That's it. So this is the idea how to calculate this thing. So using these congruent things, there's one question that I ask you to do. Okay, after that beat, just the way how to do it. I don't know. Have you done it or not? You did it. So what you calculate formula for what? For maximums or for minimums?
Oh, the formula.
Mm-hmm. I'm asking now you for to derive formula now.
Oh, we didn't derive the formula.
Okay, so now try to derive the formula, and also you may think about when you derive, so that this L, this it's very big, right? It's very big. So that distance L, right, and these are very similar, because in the big distance L and L small and L capital are very close. So we use this too.
Good here. But yeah, because what in our formula we had a formula, but in our formula we were just calculating the difference in the phase between light from the bottom slit and the upper slit.
No. Yeah, that's okay. I got. No, I want to create a formula here. How the patterns go, where the maximums and minimums are on this.
So the assumption was something you didn't tell us before. The assumption is that L is much larger than the distance between the
No, that's okay. You may do without it with the angle and then this. Just take into consideration L and L very similar, close, and talk about this distribution. This distribution where the maximums are and where the minimums are. Actually, maximums. Okay, minimums. So where the amplitude, amplitude is small, they are called nodes. Minimum are called nodes, and maximums are called antinodes.
I think it's like Crescent from now or something. No.
And we were talking about standing waves, but we already missed the point. Okay, so we too many questions. So this is for calculation. But that's already there. I asked the previous thing.
Okay, it's the same as the first question.
Yeah, it's the same thing.
We use the present, but the difference that L is really large. We can write down the same as the previous first question, but L. I don't know.
What's the difference if L is large? I don't know if it's
Because then the distance between the slits will not matter. Remember how I said it depends on the wavelength, the distance between the screen and the wall, and the distance between the slits? Well, it doesn't matter when the L is really large. It matters, but the effect is negligible. And that's the trick about physics. It's not precise.
Okay, I should say a couple of words about this, right? About standing waves, because there was a. I'm sorry, but I will say. The standing waves, actually, it is the result of superposition of two waves, which are going directions this way and that way. So one wave goes this way, another wave reflex goes back and forth. So we have a string which is fixed in two places now. There are two walls. Maybe a string, or maybe the sound wave, or maybe the wave in the ocean, which goes from two walls back and forth. This situation is called resonator. Then the wall is called resonating. Because there are very interesting things are happening here. You understand that here the amplitude of the wave cannot be anything except zero, right? So amplitude is zero here and here because nothing is moving in this point, right? And this point and this point. And the two waves, I would not explain right now. You may think about it yourself if you want. It's a little more complex in mathematics. Not that complex, but still for you it's a little more complex. But the result of two waves going this way and that way. So two waves. One wave goes here, another wave goes there. This way and that way. And they're reflecting. And they create an interesting thing which is called standing wave. Standing wave, the easiest standing wave is like a string. It's string which vibrates like this. Here no vibration, here no vibration, here the maximum. Like any string, like in guitar or in the piano, there are strings there. They may vibrate this way. But also, and the length of this, it is exactly half of the wavelength, lambda divided by 2. This is the result. So this goes like this, vibrating. And it's not moving anywhere. It's just vibrating like this, up and down, up and down.
I'm sorry, you're saying amplitude is half wavelength?
Not amplitude. The length, the distance here. This is.
Oh.
Yeah. The other thing, maybe this divided by 2. So the same thing here, right? And the string goes like this. It's fixed here, and interesting enough, it's not moving here too. It's not fixed here, of course, but it's not moving. And if you put your finger here in the middle of such vibrations, the string goes like this, you know, up and down, like this. It's not moving anywhere, just moving up and down. It's not going this or this. And still it's the superposition of two waves going this and that way. And here it is, it's each thing is lambda divided by 4. And here lambda divided by 4 too. So this is another wave, standing wave again. It's called standing because it's not moving this direction or back. It's only vibrating like this. And also another case which you have 2 points like this and it goes like this. And again you have 2 points which are not moving at all, but these parts are moving up and down in the same thing. And the whole, yeah.
So those points aren't actually really equal because of the one that's closest to the front is going down while the one to the left of it is going up.
No, they're not going down. That's what Dad is saying.
No, this when this goes up, this goes down, and this goes up too.
That's the trick about standing waves.
Yeah. You may look at them if you have a guitar. You may find out. Interesting enough that if you have that kind of thing, you can put your fingers here and here, so fix these points, and still the standing wave will be doing fine. But the same, because the same thing happens here as happens here on these walls. So in the standing wave you can fix the parts of the string and it still be vibrating. Okay, no problem happen with this. So this is interesting, very interesting stuff. You think about it, and I will have a question. And the formula is actually like this, but that's one of the questions that I wanted you to somehow derive, if you can. Okay.
Sorry, what is it? Is it a question?
No, it's not a question. I'm just talking about standard. The question now. You're ready, right?
Yeah.
To write.
Wait, I'm not ready. Okay, I'm ready.
Okay, so again, these points, the fixed points, they are called nodes. So this is node, okay? This is node and this is node. The fixed points which are not moving, they're called nodes. The moving parts are called antinodes. So these maximums.
But dude, I thought all points were fixed.
No. Only those points on the line that Dad pointed out.
Oh.
So these, all of them, 1, 2, 3, and more. There are many more. Could be many more. They called here too. They called antinodes. So maximums are antinodes. Minimums where nothing is moving is called nodes. Okay. So the first question. Try to derive formula according to your understanding what was going on. Not maybe like strict thing, but just try to understand what formula can describe this thing for antinodes for standing waves.
What formula can what, sorry?
For antinodes. This formula, x equal n lambda divided by 2 when n is 0, 1 or whatever, this is for nodes, for these fixed points. You may write it if you want, but you can find it anywhere too. This is for nodes, for fixed, sort of fixed points, or somehow fixed. They're not maybe fixed or maybe not fixed, whatever.
What's the question?
And the question is the formula for antinodes, for the maximums.
But what exactly are you looking for? The amplitude, the location? What?
No, location, of course, location. This is x, this is x-axis. X-axis, this is x-axis.
How far from the wall?
No. Yes, how from the wall? Yes. Here, like for example, here is 0. Here is some coordinate, right? So.
Okay. So the formula for
Like
nodes,
this, x, right? This is from 0 to x, right?
the formula for nodes in a standing wave.
Yeah. For no antinodes.
Oh, antinodes?
This is nodes. I already wrote it for you. For nodes. You may try to derive it too. This is for nodes, and I ask for antinodes.
And antinodes are the moving ones, right?
Antinodes, yeah, they are moving. Yes, maximums, maximum vibration there. Yep.
Yeah.
Maximum, not the moving. Many points are moving, but some of them are moving with the greatest amplitude, right? So these are antinodes. Wrote it? Okay, second question. Calculate nodes. Nodes. Now, nodes. So minimums. Nodes. For two-slit experiment. Actually, we talk in the process, right? We talk about it. So calculate it now. Nodes for two-slit experiment.
Hold on. What? Is it because the waves going through the slits will bounce back and bounce back and forth between the wall and the screen?
No, they're still there. They're still there. Maximums and minimums, nodes and antinodes. But just think about it and calculate. Okay? It's the same thing. It's two-slit experiment is true about superposition of the waves. It's actually very close. Just if you think about it, very close about this.
Yes.
And also just think about it. And the third question is try to explain and calculate if you can somehow, at least something. Try to explain and calculate at certain distance. Why? Calculate why at certain distance and calculate this distance, right? Why certain distance there's a bright spot in the middle of the shadow. So you have this disk. It is a disk, right? Not transparent. And you have waves coming here, right? This way. Like the waves with the wavelength lambda, right? And then you have somewhere the screen, right? And in the screen, of course, there's some shadow here, right? So waves going some way. There's a diffraction here, remember?
Yeah.
Waves go here, and here, if you look at the screen, you see something like this. This is the shadow. But in the middle of the shadow, somehow, so this is shadow. But here is a bright spot. At a certain distance, there is a bright spot right in the middle of this shadow.
Isn't it identical to the slit experiment?
You think about it. So somewhere here is bright spot, and here is like shadow, and here is shadow. Shadow, and bright spot.
Right.
So try to calculate it and to understand what is going on. Why? First of all, why it happens.
Same as the slit experiment, right?
It's very close, of course, but think about it. How? What is going on there? Okay? Good idea, right?
Yeah.
Okay, guys. Any other questions?
Yeah. No. Hold on. I think we got it.
You got it?
Yeah. Hold on a sec. Let me
Sure. I'm waiting.
Hold on a sec. So, formula for antinodes for standing waves, okay. Calculate nodes for two-slit experiment.
Mm-hmm.
Okay, and the third one, chunky.
That's tiny.
Is that why?
Why? There is a bright spot at a certain distance. Bright spot right in the center of the shadow. We have a disk.
Yeah.
Waves.
Yeah, got it.
What happens? And try to calculate something here. Okay, guys, that's it.
Okay, thank you.
Okay,
Love you.
have fun. Love you.